The question says that a small candle 2.5 centimeter in size is placed at 27 centimeter in front of a concave mirror of radius of curvature 36 centimeter. At what distance from the mirror should a screen be placed in order to obtain a sharp image, and describe the nature and size of the image? If the candle is moved closer to the mirror, how would the screen have to be moved? So in this question, a concave mirror is given of a defined curvature, radius of curvature, and the object distance from the pole of the mirror is given, that is 27 centimeter, and the height of the object is given, that is 2.5 centimeter in size. At first we have to find out at what position should the screen be placed so that we can obtain the sharp image. So in a simple terms, it is asking the position V of the image from the mirror. And the second question is saying that describe the nature and size of the image. And the third question is, if the candle is moved closer to the mirror, how would the screen have to be moved? So the third question is saying that if we move this candle towards the mirror, then how would the position of this image? So let us proceed. So we can use the mirror formula over here, which is given by 1 by f equals to 1 by u plus 1 by v, where f is the focal length and u is the object distance and v is the image distance. So focal length of this mirror is given, that is of 36 centimeter by 2. So we can find out the focal length as 18 centimeter. Object distance is given, since it is in front of the mirror, so u is going to be negative, and it is going to be negative of 27 centimeter. So using this formula, we can calculate the value of v, because only v is unknown over here. So after we get the value of v, we can use it in the formula of magnification. So magnification we will get by minus of v by u, where v is the image distance and u is the object distance. So let's calculate the value of v first. So substituting the values of u and f in this equation, we get the value of v, that is v equals to minus of 54 centimeter. That is, the position of image is in the same side of the mirror as that of the object, because it is negative in size. Now we can negative in magnitude. Now we can calculate the value of m, that is minus of v by u. So substituting the values of v and u in this formula, we will get a value of minus 2, that is, the object is magnified and it is real. We can also see from the image diagram over here. So the at first we have taken the parallel to the principal axis, the array parallel to the principal axis, which is reflected passing through the focus, and the second ray is taken passing through the center of curvature. So it will retrace the incident ray, and since two ray must meet to form an image, so the image will form over here with a value of v equals to minus of 54 centimeter. Now we have got the value of v, that is where should the screen be placed. We have to find out what is the nature and size of the image. So since we have got the value of m, we can find out the we can find out the size of image, that is equals to magnification times the original size of the object, that is 2.5 times 2, that is 5 centimeter. And nature is real, the image is real. And now we have to find out, if the candle is moved closer to the mirror, how would the screen have to be moved? So that is, if this candle is approaching f and also approaching pole, then how would the position of image be moved? So let us make the diagram over here. So at first case, we assume that the candle has been placed at focus. So we see that these two rays have become parallel. So the image will be forming an infinity. So we can say that if the candle is moved towards the focal length, the position of image will be towards infinity. And if the candle is moved beyond f towards the pole, so we can see that the image is forming, that is virtual. No real image can be formed over here, and it is virtual and it is magnified. Thank you. The question says that a 4.5 centimeter needle is placed 12 centimeter away from the convex mirror of focal length 15 centimeter. Give the location of the image and the magnification. Describe what happens as the needle is moved farther away from the mirror. So here the height of the object is given, that is 4.5 centimeter, and the value of the position away from the mirror is also given, that is of 12 centimeter, and the focal length of the mirror is also given. So we have to find out the location of the image, that is the value of v, and the value of m, that is magnification. So we know from the mirror formula that 1 by f equals to 1 by u plus 1 by v, where f is the focal length and u is the distance of the object from the mirror, and v is the distance of image from the pole of the mirror. And the value of the formula for magnification is minus of v by u. So let us substitute the values. We have been given the value of u, we have been given the value of f. We have to find out the value of v, that is the position of image. So since focal length of convex mirror is positive, so f would be equal to plus of 15 centimeter and u would be equal to minus of 12 centimeter. So finding the unknown v, we will get the value of 6.67 centimeter. Now we have to find out the magnification, so we will substitute the value of u and v in this magnification formula, and we will get the value of equals to plus of 5 by 9. Now let's revisit the ray diagram. Here we have taken two rays from the top of the needle. So one would be along the center of curvature, so it will retrace its incident path, and the another parallel to the principal axis, so it will reflect along the focus of the convex mirror, and if we retrace it behind the mirror, we will get a virtual image. So the nature of image is virtual. The image is diminished because the value of m is less than 1, so the image will be diminished, and the size of image we can calculate with the value of magnification, and the formula is magnification multiplied by original size of the object, and we will get the value of 2.5 centimeter. So we can also see that as the object distance is increased, or as the needle is moved away from the mirror, the image will tend towards the focal point, diminishing in size. Or if we move this object away from this mirror, so this image will move towards the focal point, and the magnification will reduce more and it will become more diminished. Thank you.
This question talks about the apparent height and the real height problem. So in this question there is a beaker and it is filled with water at first, and the height of this beaker is 12.5 centimeter, and at the bottom of the beaker there is a needle, and if you see from the top, then the needle is appearing to be at a depth of 9.4 centimeter. That is the apparent height of this needle is going to be 9.4 centimeter when the beaker is filled with water. We have to find out what is the refractive index of water from the given data. So we have been given the real depth of the tank, that is 12.5 centimeter, and the apparent depth, that is 9.4 centimeter. Now we know that refractive index can be related by real depth and apparent depth, as the refractive index would be equal to real depth by apparent depth. So we have to find out refractive index of water at first. So the real depth is 12.5 centimeter and the apparent depth is 9.4 centimeters, so the refractive index would come out to be 1.33 centimeter. Now the question was saying that when the water is replaced with the fluid of refractive index 1.63, then what would be the apparent depth? And it is not asking directly what is the apparent depth, it is asking by what distance will the microscope move so that it can focus again. So in a nutshell, it is asking what is the apparent depth, what is the new apparent depth. So if we replace the value of refractive index to be 1.63 now in this formula, then we can find out apparent depth, as we have been given the real depth, that is 12.5 centimeter. So apparent depth would be equal to 12.5 centimeter by 1.63. Now if we calculate this, then we can get a value of 7.67 centimeter. So the new apparent depth is going to be 7.67 centimeter if the water is replaced by another liquid. Now this means that the previous apparent depth was 9.4 centimeter as given. Now the new apparent depth is going to be 7.67 centimeter. So the question was asking that what distance should we move the microscope so that it can focus again. So the difference of these two apparent depth is the distance by which we need to move it so that we can focus again. So the difference between 7.67 and 9.4 centimeter is going to be equal to 1.73 centimeter. Thank you. The question says that the figure 9.27 A and B show refraction of a ray in the air incident at 60 degree with a normal to the glass air and the water air interface respectively. Predict the angle of refraction in glass when the angle of incidence in water is 45 degree with the normal to the water glass interface. Now we have been given two cases. of air glass interface and water air interface, and we have to find out what is the angle of refraction in the glass water interface when the ray is incident in the water and going to the glass media. So we will use Snell's law over here. Here for convenience I have taken the refractive index of glass as N1 and refractive index of air as N2 and refractive index of water as N3. Now let's revisit the Snell's law. So it says that when a ray is moving from one media to another, let's say that it is incident in the media of refractive index N1 and it is going in the media of refractive index N2, and it is making an angle of I with the normal in the incident media, and it is going to make an angle of R. So by Snell's law we know that N1 sine I would be equal to N2 sine R. Now we will use this in order to find the alpha, that is the angle of refracted ray in the glass media. So using Snell's law in the first diagram we see that N1 sine 35 degree is going to be equal to N2 times sine 60 degree. Similarly equation 2 we will get from the second figure as N2 sine 60 degree is going to be equal to N3 sine 47 degree. Now similarly we will see here that N1 sine alpha is going to be equal to N3 sine 45 degree. Now solving equation 1 and 2 we will get N1 sine 35 degree is going to be equal to N3 sine 47 degrees. Now we will use this and the third equation to find out the value of sine alpha, because we can cancel out N1 and N3 from these two equations. So by dividing equation 3 by 4 we will get sine alpha by sine 35 degree is equals to sine 47 degrees by sine 45 degree. Now substituting the values we will get sine alpha is equals to 0.6 approximately, and now if we take inverse then we will get a value of 36.8 degrees. So we see that the value of alpha is going to be equal to approximately 36.8 degrees. Thank you. The question says that a small bulb is placed at the bottom of the tank containing water at a depth of 80 centimeter. What is the area of surface of water through which light from the bulb can emerge out? Refractive index of the water is 1.33, and we have to consider the bulb as a point source. Now here we see that it is a water tank. I have symbolized it with the black ink. It is 80 centimeter deep, and in the bottom of the tank there is a bulb which is a point source of light, and we have to find out of what surface area the light will come out. So we will use here the theory of total internal reflection. If we assume there is a ray that is emerging out of the bulb and it is making an angle of I, so in order for that ray to emerge out, it should be less than the critical angle. We know that the critical angle is defined as the angle of incidence, which provides 90 degree to the angle of reflection. That is, if IC is the critical angle, then the refracted ray would not cross the interface and it will just remain on the boundary like this, OA, and the ray will be on the boundary. And if the angle of incidence is greater than critical angle, then the ray will be refracted in the same media. And if it is less than IC or the critical angle, then the ray will come out. Now we have to find out in what area does the ray come out of the tank. Now, since using the Snell's law, we can say that mu of water and sine of I would be equal to, we first will find out the critical angle. So IC will be equal to, let us, the refractive index of the air is 1, so 1 times sine 90 degree. This is 90 degrees, so we will take 90 degree. Now we will find out sine IC. Now this will give us sine IC equal to 1 by 1.33, because we know that mu is 1.33. Now if we figure out what is IC, then IC will be sine inverse 1 by 1.33, and this will come out to be equal to 48.75 degree. So we have got a value of IC in this triangle AOB. We have got the value of IC. Now in order to find out this area, we must know the radius, that is OB, so that we can find out the area. Now radius OB can be found out using the trigonometric relation, that is tan of IC, that tan of IC would be equal to the perpendicular, that is OB, divided by AB. Here we have to find out OB. We know that AB is the height, that is 80 centimeter, which is given. OB would be equal to tan of 48.75 degrees multiplied by AB, that is 80 centimeter, and which will give us something around 91.2 centimeter, that is radius of the circle. Now in order to find out area, we can use the formula of area of circle, that is pi r square, and which will give us 26110 centimeter square, or we can say that 2.61 meter square. The question is saying that a prism is made of a glass of unknown refractive index. A parallel beam of light is incident on the face of the prism. The angle of minimum deviation is measured to be 40 degree. What is the refractive index of the material of the prism? And the refracting angle of the prism is 60 degree. If the prism is placed in water, refractive index of 1.33, predict the new angle of minimum deviation. So here we have been given the value of minimum deviation. Let us symbolize it with dm. We have been given it is the value of 40 degree. We have to find out the refractive index of this prism, and one more thing we have been given, the refracting angle of the prism, that is the vertex angle, it is given as 60 degree. So we can symbolize it with A as 60 degree. Now we know why the definition of the minimum deviation, that dm is equals to 2 times I minus A. I is the angle of incidence and it is equals to the angle of emergence for the minimum deviation. We know that the refractive index of the prism is given by sine of A plus dm by 2 divided by sine of A by 2. Now here we have been given the value of A and dm both. So we can simply put it as sine of A plus dm would be equal to 100 by 2, that is 50 degrees, and the value of A is 60 degrees, so it will be equal to sine of 30. Now this will give us a refractive index of 1.53. So we have successfully found out the refractive index of the prism. Now we have to find out what if the prism is placed in water. What will be the new angle of minimum deviation? Refractive index of the prism, that is 1.53. This formula will turn out to be 1.53 by that of the incident media, that is on the water, 1.33. This will give us sine of A. It will be constant because the prism is same, and that is 60 degree, plus dm we have to find out. So dm will be unknown, by 2 divided by sine of A by 2, that is 30 degree. Now after solving this, we will come to a conclusion that dm is equals to 10.32 degree. So here this formula is used. Here the refractive index is refractive index of the prism with respect to the media in which the prism is kept. That's why we use this formula in the case of water, that is the refractive index of prism with respect to media in which the prism is kept. The question is saying that here we have to manufacture a double convex lens from the glass of refractive index of 1.55, and we have been given the focal length that is required, and it is of f equals to 20 centimeter. Since we know the lens maker's formula, we will be applying it over here. It is saying that we have to make a double convex lens of focal length equal to 20 centimeter. So we know the lens maker's formula, that is 1 by f equals to n minus 1. Here n is the refractive index of the glass with respect to the media in which it is kept, 1 by r1 minus 1 by r2. Here r1 and r2 are the radius of curvature of this side versus this side. Substituting the values, we will get, since it is a convex lens, so focal length is going to be positive. So 1 by 20 would be equal to, refractive index is given, that is 1.55 minus of 1 by r1. Here r1, the radius of curvature is measured from the right hand side because it is curved, and its center would be in the right side, so it is going to be positive. So 1 by r Since R1 and R2 magnitude is going to be same because it is given over here with the both faces of same radius of curvature. So R1 would be equal to R2 in magnitude minus R2. Since the center of the R2 curvature is going to be on the left hand side, so we will term it as 1 by minus R. Here after solving this, we will get 1 by 20 centimeter is equals to 0.55 multiplied by 2 by R, and this will give us the value of R as 22 centimeter. So the radius of curvature of the glass required is 22 centimeter. Thank you. A beam of light converges at a point P. So let us assume that this is a point P and a beam of light is converging at this point from the left hand side. And what if we keep concave lens and convex lens? The first is convex lens of focal length 20 centimeter, and the second case we have got a concave lens of focal length 16 centimeters. So here f is equals to plus 20 centimeter and here f equals to minus of 16 centimeter. Now the distance between these two is 12 centimeter, that is given. So we have to find out where will the beam converge. So in the first case, we will use the lens formula, that is 1 by f equals to 1 by v minus 1 by u. Here object is virtual, that is light was coming to that point but now it is obstructed, so it is virtual. So 1 by f is equals to, in this case, that is in convex case, 1 by f is going to be 1 by 20. 1 by v, we have to find out 1 by v, and u is 12 centimeter plus of 12 centimeter. So here solving this, we will get a value of 1 by v as 2 by 15 or v as 7.5 centimeter. So what we see here is that, and it is at 7.5 centimeter away from the lens of this convex lens. Now in the second case, we have got a concave lens. Here again, we have to find out the distance, where will the light converge. So here again, we will use the lens formula, that is 1 by v, 1 by f equals to 1 by v minus 1 by u. Now the focal length in the case of concave lens is negative. So we will use 1 by minus of 16 centimeter equals to, we have to find out the image distance, 1 by v minus object, that is virtual, and it is again 12 centimeter away from the pole of the lens. So, and the distance is going to be positive, so we will use 12 centimeter over here. Now solving this, we will get 1 by v is equals to 1 by 48, that is v equals to 48 centimeter. So again it would be 48 centimeter to the right of the lens, and in the first case it was 7.5 centimeter to the right of the lens. The question is saying that an object of size 3 centimeter, that is the height of the object is given 3 centimeter, is placed 14 centimeter in front of the concave lens. Here concave lens, the subject is concave lens and the object distance is 14 centimeters. So we can write u equals to 14 centimeter in front, that is minus for 14 centimeter would be there, and concave lens of focal length 21 centimeters. So here f is going to be equal to minus of 21 centimeter because it is concave lens. Now describe the image produced by the lens. We have to find out image, and we have to describe the image. It means we have to find out v, and we also need to find out m because that tells us the nature of image, that is whether it is diminished in size and it is virtual or not. So we have to also comment on what happens if the object is moved further away from the lens. Now what if the object is moved, this object is moved away from the lens, or it is moved on the left hand side, what will happen to the image? Now let us first use the lens formula over here. We will find the value of v, then we will find the value of n, and then we will comment on the nature of the image. So using the lens formula, we have got 1 by v minus 1 by u equals to 1 by f. So here 1 by v would be equal to 1 by u, that is 1 by f is minus of 1 by 21 centimeter, and then u will go on that side and that too is negative, so it will remain negative of 1 by 14 centimeter. This will give us the value of 1 by v equals to minus of 5 by 42. Thus the value of v is going to be equal to minus of 8.4 centimeter. So the image is on the left hand side of the lens because we have got a value of negative v. Now let us try to find out the value of magnification. Magnification for the lens is defined as v by u. So substituting the values, we will get minus of 8.4 centimeter divided by the value of u is 14 centimeter, minus of 14 centimeter, and this will give us a value of 0.6. So here magnification is less than 1, that is the image will be diminished, and it is positive, magnification is positive. That means the object is going to be virtual and is going to be irrelevant. Now let us comment on what happens if the object is moved further away from the lens. Now let us first draw roughly the image, the ray diagram of this. So here let us assume that this is the focus. So a ray parallel will go on from here, and then it will appear to diverge from the focus, and the second ray will go from the center. Now the image will be somewhere like this. Now as we move this object away from the focus or away from the lens, let's assume that the object is placed over here. So what we will see is the image will tend towards the focus, because this parallel ray is going to be going in this direction only, but the second ray like this. So we will see that the magnification will drop further on, and as u is increased to infinity, the image distance v will tend towards the focus and the magnification will tend towards 0. Here the question is saying that what is the focal length of the convex lens of focal length 30 centimeter in contact with the concave lens of focal length of 20 centimeter. Is the system converging or diverging lens? Ignore thickness of the lenses. So we have been given thin lenses, and we have to find out what is the effective focal length. Now we know that the focal length, effective focal length, is given by 1 by f effective is equals to 1 by f1 plus 1 by f2 plus so on. Here we have been given only two lenses, so we will take f1 and f2 only. Now here f1 in the case of convex lens is positive, and f2 in the case of concave lens is always negative. So let us calculate the value of f effective, and that is going to be equal to 1 by f1, that is 1 by convex 30 minus of 1 by 20. So after adding this, we will get a value of minus of 1 by 60 centimeter. So focal length effective is going to be equal to minus of 60 centimeter. So here we see that the focal length effective is negative. That means it is diverging in nature, or we have got a concave length of focal length 60 centimeter. The question says that a compound microscope consists of an objective lens of focal length 2 centimeter and an eyepiece of focal length 6.25 centimeters separated by a distance of 15 centimeter. How far from the objective should an object be placed in order to obtain the final image at the least distance of the distinct vision, that is 25 centimeter, and at infinity? What is the magnifying power of the microscope in each case? Now here we have been given a compound microscope of which objective has a focal length of 2 centimeter and the eyepiece has a focal length of 6.25 centimeter. We have to find out how far from the objective should an object be placed. Like we have to find out the value of u objective in the case VE, that is the image formed by the eyepiece is at minus d. D is the least distance of distinct vision, that is 25 centimeter, and the second case is that VE is equals to infinity, that is the image is forming at infinity, which is good for relaxed eye viewing. Now we have to also find out what is the magnifying power of microscope in each case. We have to also find out the value of m. Now we will use two formulas in this question. The first is lens formula, that is 1 by v minus 1 by u equals to 1 by f. Here I have represented v, fe and fo as a focal length of eyepiece and the objective respectively, and subsequently u and v has been also represented with the subscript of e and o, as e as the eyepiece and o as the objective. Now let us move towards the first case where the image is forming at the least distance of distinct vision, that is 25 centimeter. So we know that in a compound microscope, an object is placed over here in front of objective. Now this will form a virtual image between these two lenses, let us say over here, and this virtual image will be treated as a virtual object for eyepiece, and this eyepiece will form the final image, which is somewhere magnified. Now we have to find out the value of u naught in both the cases. So in the first case, the least distance of distinct vision, the image is forming, that is the final image, VE is forming at minus d. So we will use the lens formula for the eyepiece. We have been given the value of VE over here, that is minus of d, that is minus of 25 centimeter. So using the lens formula for the eyepiece, we have got 1 by VE minus 1 by UE is equals to 1 by FE. So d here 1 by V is minus of 25 centimeter. Now 1 by UE is equals to 1 by 6.25. We have been given the value of FE, that is 6.25. and since it is a convex lens, so Fe is going to be positive. Now solving for this, we have got a value of Ue as minus of 5 centimeter. So it means that the object for the eyepiece should be at minus of 5 centimeter, or with proper sign convention, the object should be here with a distance of 5 centimeter from this pole of this lens, that is 5 centimeter. Now for the image to form at minus d, the object should be here. Now for this lens, what is the distance between this lens and this image? So the image by the objective is going to be treated as the object for this eyepiece. So if the object should be at here, that is at 5 centimeter from the left of the lens, then the image formed by the objective should be at 10 centimeter on the right side of this lens. So V naught, that is the image distance for this objective, should be equal to 10 centimeter. So V naught or the VO is equals to 15 centimeter minus 5 centimeter, that is 10 centimeter. So we have got a value of FO, we have been given the value of FO, that is the focal length of the objective, that is 2 centimeter. We have to find out the value of UO, that is the object distance from the objective. So using lens formula again, we have been given the value of FO and VO, and we have to find out the value of UO. So solving this, we have got a value of U as minus 2.5 centimeter. So the solution of first case is here, that is if the object is kept at 2 centimeter from the lens of the from the left of the objective, then we will get a final image at a distance of 25 centimeter from the left of this eyepiece. Now we have to find out the value of magnification. So magnification in this case, we know the formula for magnification is given by VO by UO multiplied by D by UE. So here VO is the image distance from the objective and UO is the object distance from the objective. D is the distance of distinct vision and UE is the object distance from the eyepiece. So we have all the values over here. We will substitute it and we will get a value of 20x. So when the image is forming at the least distance of distinct vision, then we are getting a magnification power of 20. Now in the second case, the question was final image at infinity. That is, the final image formed by this eyepiece is going to be at infinity. So we know for image to form at infinity, the object will place at the focus. So UE, that is object for the eyepiece, is going to be minus Fe, and we have been given the value of Fe, that is 6.25 centimeter. Focal length of the eyepiece, that is 6.25 centimeter. So let us find out the distance of VO. Distance between the two lenses is 15 centimeter. So VO plus UE, that is, let us understand with this diagram. VO plus UE. VO is the image formed by the objective. VO is the image formed by the objective plus UE, that is, that image is going to be the object for the eyepiece. This will always be equal to 15 centimeter because the distance between the lens is fixed, 15 centimeter. So using this, we will find out the value of VO, that is the image distance from the objective, and this will give us a value of 15 minus 6.25, that is 8.75. Since this is from the right of the objective, so this will be positive. We will put it in the lens equation again, and for finding out the value of UO, so for solving this question, we will get the value of UO as minus of 2.59 centimeter. Now we have got the data for the second case as well, that is when the image is forming at infinity. So using the formula, same formula for magnification, that is VO by UO into D by UE, we will get a value of magnification as 13.51 x. That is, the magnifying power is less when the image is forming at infinity as compared to when the image is forming at the least distance of distinct vision, that is 25 centimeter. I hope you understood this question. The question says that a person with normal near point 25 centimeter using a compound microscope with objective of focal length 8 millimeter and eyepiece of focal length 2.5 centimeter can bring an object placed at 9 millimeter from the objective in a sharp focus. What is the separation between the two lenses? Calculate the magnifying power of the microscope. So in this question, it is simply asking that what would be the distance between these two lenses such that if object is placed at 9 millimeter or 0.9 centimeter in front of the object, the person with a normal near point of 25 centimeter sees that object clearly. So it is simply asking what would be the length between, what would be the distance between these two lenses such that the person can focus it, or the eyepiece can create an image at V equals to 25 centimeter in front of it. So in order to get the length between these two lenses, we will have to find out the distance between the image created by the objective, that is V naught, and the distance between the image and that eyepiece lens, or we can term it as object length, UE. So length will be composed of V0, that is the image distance between the objective lens and the image, and UE, that is the object distance from the eyepiece. That will give us the answer. Now we have to also calculate the magnifying power of the microscope. So in order to find out V0, VO, and UE, we will use the lens equation. So we know that using the lens equation on the objective, we know that 1 by V0 minus 1 by U0 is equals to 1 by focal length of that objective. Now using these values that are given for VO, that is 9 millimeter, we will use it as minus 1 by 0.9. So we will get V0 as 36.5 centimeter. Now what is left is calculation of UE, that is the object distance between the eyepiece and the image formed by the objective. So using the lens formula again on the eyepiece, we know the value of VE, that is the image must form at the least distance of distinct vision, that is 25 centimeter in front of the eyepiece, and we have been given the focal length of the objective, that is 2.5 centimeter, focal length of the eyepiece, that is 2.5 centimeter. So we only need to find UE. So upon calculation, we will get a UE is equals to minus of 25 by 11. Now the length, as we saw earlier, would be composed of V0 plus UE, the magnitude of these two values. So after adding these two values, we will get a distance of 9.47. That is, the length of the microscope would be 9.47 for the clear vision. Thank you. We also need to find the magnification in this case. So magnification is given by VO by UO into D by UE. So we know the value of VO over here. We have calculated it as 36.5, and UO is given, that is 0.9. The distance of the object from the objective. D is known, that is 25 centimeter, and UE we calculated to a value of 25 by 11. So after this formula, using this formula and substituting the values, we will get a result of 88. That is, the magnification of this microscope is 88x. The question is saying that a small telescope has an objective lens of focal length 144 centimeter and an eyepiece of focal length 6 centimeter. What is the magnifying power of the telescope? What is the separation between the objective and the eyepiece? So in a telescope, we know that for the image to be forming at the infinity, image formed by objective must lie on the first focus of the eyepiece. That is, if image formed by this lens is on the focal point of the of the eyepiece, then the image will be formed at infinity. That is, the total length of this telescope would be given by focal length of the objective plus focal length of the eyepiece. Now here, since the rays are approaching from the infinity, so we assume that the image is formed at the focus of the objective, the second focal point of the objective, and that image will be used as a virtual object for this eyepiece to form the image, to form the final image. Now magnifying power is given by focal length of the objective by focal length of the eyepiece, and substituting the values of 144 and 6 centimeter, we will get a value of 24x. That is, the magnifying power of this microscope is 24x. And the question about the separation between the objective and the eyepiece, so we saw earlier that the separation is given by the addition of these two focal lengths. So it will be 144 plus 6 centimeter, which will give out to be value of 150 centimeter. Thank you. The question says that a giant refracting telescope at an observatory has an objective lens of focal length 15 meter. If an eyepiece of focal length 1 centimeter is used, what is the angular magnification of the telescope? The second question says that if the telescope is used to view the moon, what is the diameter of the image of the moon formed by the objective lens? The diameter of the moon is 3.48 into 10 to the power 6 meter, and the radius of the lunar orbit is 3.8 into 10 to the power 6 meters. So first question is saying that simply we have to find out the magnification of this telescope. So we know the formula for magnification. It is given by the focal length of the objective by focal length of the eyepiece. So after substituting the values, we will get a value of 1500x. Now the second question is asking what would be the diameter of the image of the moon given the diameter of the actual moon and the distance of moon between Earth, that is the lunar orbit or the orbit in which moon rotates around the earth. That is 3.8 into 10 to the power 6 meter. So here, let us revisit the ray diagram formed by the convex lenses. So if we see that an object is beyond the focal length, then height of the object is HO and height of the image is HI. So if we focus, so these are the two rays that I have shown over here. The first rays is parallel to the focus, parallel to the principal axis, so it will go from focus to the beyond, and then the second ray is towards the pole of the lens, so it will go unaltered, and the intersection will form the image. So if we focus on the two triangles over here, that is OAB and OCD, these two triangles are always going to be similar, and we know the property of similar triangle is that the ratio of the similar sides are always equal. So in this two triangle OAB and OCD, OA by OC will always be equal to AB by CD. So this question was asking what is the radius of the moon of the image? What is the radius of the image of the moon? So if we substitute the values, if we assume that this is the moon over here, now this is going to be the radius of the moon. So we can assume that AB is the radius of the moon and OA is the distance of the moon from the earth, that is the lunar orbit, and OC is the focal length of the objective. OC is the focal length of the objective, and CD is the radius of the image. So HI is the radius of the image. So moon will be forming like this. So we can assume like this condition, and from the property of the similar triangles, using this ratio, we can easily calculate the value of CD, that is unknown over here, that is the radius of the image of the moon. So substituting the values, we will get CD equals to 6.86 into 10 to the power 2 meter. We will get a value of 6.86 into 10 to the power minus 2 meter. So we can easily calculate the diameter of the moon now. So diameter of the moon would be equal to 2 times CD, that is 13.7 centimeter. Thank you. The question says that use the mirror equation to deduce that an object placed between f and 2f of a concave mirror produces a real image beyond 2f. Now there are four similar given questions, and in each question we have to use the mirror equation to deduce the following statements. So let's continue one by one. So in the first statement, we have been given an object placed between f and 2f of a concave mirror produces a real image beyond 2f. So here is a concave mirror, and we have to use this mirror equation. We don't need to rely on the mirror on the ray diagram. I have just used the ray diagram for the illustration. So we have to prove that when the object is placed between f and 2f, that is f and 2f, the concave mirror produces a real image beyond 2f. The image will be produced beyond 2f and it will be real. That is, it will be formed by the real intersection of light, or in a simple term, it should be formed on the left side of the mirror. That is, V should be negative. V, that is the distance from the pole of the mirror to the image, should be negative using the sign convention. So let's begin. I have assumed that the distance between the focus and the object is x. That's making u, that is the object distance from the pole of the mirror, would be equal to f plus x. Now using the sign convention, u can be substituted as minus of f by f plus x. So using this value in the mirror equation, we will get 1 by v, that is the image distance, minus 1 by f plus x equal to minus of 1 by f. Here minus is because the concave mirror, its focal length using sign convention is taken negative. So 1 by v would be equal to minus of 1 by f plus 1 by f plus x. Now using simplifying this, we will get the value of v as f multiplied by f plus x by x, minus of f multiplied by f plus x by x. Now in the question, it was an object placed between f and af, f and 2f. That is, when the object is at f, x would be equal to 0. So using this x equal to 0 in this expression, we will get a value of minus infinity, that is v tend to minus infinity. And when object is at 2f, x will be equal to f. Using the value of f in the place of x, we will get a value of minus of 2x. So in this expression, we see that the image lies between minus of infinity to minus of 2f. Thus, the image is real as it is forming by the real intersection of the rays. And in the question also, it was given that we have to prove that when the object is placed between f and 2f of the concave mirror, then it produces a real image beyond 2f. and the image is also beyond 2f. The second question was, a concave mirror produces a virtual image independent of the location of the object. So a convex mirror produces, the question B was, a convex mirror always produces virtual image independent of the location of the object. So here we have been given a convex mirror, and we have to prove that it will always produce virtual image irrespective of the position of the object. So here I have assumed again u, the magnitude of u as x. So using sign convention, we can write u as minus x. Substituting in this mirror equation, we will get 1 by v minus 1 by x equals to 1 by f. Here f is positive because it is a convex mirror. And simplifying this, we will get the expression for v, that is fx by f plus x. Here we see that for x equals to 0, v is always equals to 0. That is when wherever the object is placed, that is x equals to 0, the v is always going to be positive. The image is always forming on the other side of the mirror, or the image is always virtual. Since v is positive, it means that v measured from here is always going to be in this side of the mirror, that is in the right side of the mirror. Thus there there will always be a virtual image forming for this case. Now the third question was, the virtual image produced by a convex mirror is always diminished in size and located between focus and the pole. So the question is asking us to comment on the magnification, and it is also asking us to comment on the position of the image that is lying between the pole and the focus. So from the above calculation for v, we see that v is equals to fx by f plus x, and if we divide both the terms, both the numerator and denominator by x, we will get f by x plus 1. So when we increase the value of x over here, then we see that this term is going to be 0. This term will tend towards 0. Thus the maximum value of v that we can achieve would be v equals to f. That is, if we increase the value of x, then v will approach to f. That is, if we take the image away from the mirror, if we take the object away from the mirror, then the maximum position of the image is going to be at f. That's what the question said. Now we have to comment on the magnification in this case. Now magnification, we know that it is given by minus of v by u. So we will substitute it in the given formula, that is minus of v fx by f plus x into into 1 by u, that is 1 by minus x. So equating this, we will get f by f plus x. Now here we see that as x increases, f by f plus x is always going to be less than 1. That is, the object, that is the image will always be diminished. And m is always going to be positive, that is the virtual image will always be erect. Now let's focus towards the last question. Last question said that the object placed between pole and the focus of the concave mirror produces a virtual and enlarged image. Virtual and enlarged image. We have to prove that. So let's assume that the distance between the object and the pole of the mirror is x. Now using sign convention, we can write u as minus of x, and I have substituted it in the mirror equation, 1 by v plus 1 by u equals to 1 by f. So 1 by v minus 1 by x equals to minus of f, because it is a concave mirror. Now again solving for v, we will get the value of v as fx by f minus x. So now for u equals to minus f x equals to f, that is, using this value of x in this expression, we will get the value of v as infinity. That is, when the object is at focus, the image will be at infinity. Now for the case when u is between f and 0, or the object is between focus and the pole, we will get a value of v as positive, because x will always be less than focus in magnitude. Thus this both term is going to be positive, thus v is going to be positive. And what it means that v is positive, we see that if v is positive, the mirror will always form the image in the right side of the mirror. That's why we can say that the image will always be virtual. Now let's comment on the magnification. So substituting the values of v and u in the magnification formula, we will get the value of m as f by f minus x. Now since f minus x will always be less than f, thus the value of m will always be greater than 1. Now here you should mark that I have used the sign convention for x over here, so x will always be positive over here. So that is why f minus x will always be less than f. So m will always be greater than 1 or the image will always be enlarged. That's how we have proved all those four statements that were given using the mirror formula. Thank you. The question is saying that a small pin fixed on a tabletop is viewed from above from a distance of 50 centimeter. By what distance would the pin appear to be raised if it is viewed from the same point through the 15 centimeter thick glass slab held parallel to the table? Refractive index of glass is 1.5 centimeter, 1.5, and does this answer depend on the location of the slab? So here there is a pinpoint on the slab, pinpoint on the table, and there is a slab through which an eye is there or a person observer is there, and it is viewing the pin top. Now we have to find out by what distance will this top be appear elevated. Like since the actual distance is 50 centimeter, then by what distance will it appear elevated because of this glass? So we know the formula for apparent depth or apparent length in this case, because the light is traveling from a different media, so there will be apparent shift. Now length apparent would be given by d1, that is the thickness of the glass, divided by mu1, that is the refractive index of this glass. Now substituting the values, we will get apparent depth of 10 centimeter. What means is that though the thickness of glass is 15 centimeter, but it would appear as if it is just 10 centimeter. So there will be a shift of 15 minus 10 equals to 5 centimeter, or the pin top will appear to be have moved 5 centimeter above. So we can say that the pin appears not to be at 15 centimeter as the thickness of the block rather than 10 centimeter. So the pin appears to be raised by 5 centimeter. The question is saying that figure 9.28 shows a cross section of light pipe made of a glass fiber of refractive index 1.68. The outer covering of the pipe is made of material of refractive index 1.44. What is the range of the angle of incident rays with the axis of pipe for which the total internal reflection inside the pipe takes place, as shown in the figure? What is the answer if there is no outer covering of the pipe? So this is a glass pipe in which ray of light is traveling. Now we have been given that this is the angle of incidence by which the ray enters, and this is the angle of refraction, first refraction, and we have to find out the condition over which what would be the angle of incidence for which total internal reflection takes place. That is, the light doesn't pass through the outer covering, it reflects totally inside. What is the criteria for total internal reflection for this interface, that is the outer covering and the glass interface? Now we can apply Snell's law over here. Now this is the first part of the question, like we have to find out what is the range of I, this I. Now the second part of the question says that what if we remove this outer covering, then we have to find out the range of I. So we will be using Snell's law over here. Now let's revisit the Snell's law. So it says that if the angle of incidence in one media of refractive index n1 and the angle of refraction in the other media of refractive index n2, then it can be related by n1 sin I equals to n2 sin R. So we will use this Snell's law in order to find out the critical angle. So let's calculate the critical angle. So using this Snell's law over this diagram, we can say that we can see that sin IC equals to sin inverse mu2 by mu1, where mu2 is the refractive index of the glass outer covering and mu1 is the refractive index of the inner core of the glass. Now this will give us IC as 59 degree, that is critical angle of 59 degree. So by now we have come to know that IC, that is I dash must be at least 59 degree for the total internal reflection to take place. Now the minimum value of I dash is 59 degree. So in this triangle we can easily find out what should be the value of R so that total internal reflection takes place. That is, if this angle is 59 degree, then what would be the value of R? So we know that this is a right angle triangle. So I dash plus R must be equal to 90 degree. So R plus 59 degree must be equal to 90 degree. So the value of R must be equal to 31 degree. So the minimum value of I dash should be 59 degree. So maximum value of R should be 31 degree. Now for this value of R to be 31 degree, what should be the angle of incidence? Again we will apply Snell's law over here. Now we can take the refractive index of this media as 1, and we know the refractive index of this media, that is the glass core media, as 1.68. So we will apply Snell's law over here. So calculating the condition for r that is less than 31 degree would be 1 sine I is equals to 1.68 sine r. Now sine I by sine 31 degree, that is sine r, I have written sine 31 degree, would be equal to 1.68. Now this will give us sine I equals to 1.68 times 0.52. Now 0.52 is the value of sine 31 degree. I have substituted it over there. Now the value of I would be equal to approximately 60 degree. That is, for the angle of incidence of 60 degree, we will get a value of angle of refraction in the glass core as 31 degree. Now, the angle of refraction must be less than 31 degree in order for the total internal reflection to take place. Now, if we increase this value of I, then obviously the angle of refraction will also increase. So, the angle of incidence must be less than 60 degrees so that the angle of refraction doesn't surpass 31 degree, or the IC or I dash, the value of I dash shouldn't decrease from the critical angle, because if the value of I dash will decrease from the critical angle, then the total internal reflection will not take place. Now we have found out the condition for total internal reflection to take place, that is I should be less than 60 degree and greater than 0. Now let's cover the case when there is no any outer covering. Now in this case we can assume that mu2, that is the value of outer covering, refractive index of outer covering, mu2 is equals to 1. Now in this case we will see that again we will find out the value of IC using the Snell's law. So we can write over here that I1 sin IC equals to mu1 sin IC equals to mu2 sin R. Now R is the angle of refraction over here and IC is this one. So substituting the values of refractive index, we will get 1.68 into sin IC is equals to sin 90 degree. R is 90 degree over here. So we will get a value of IC as 36.5 degree. Now for total internal reflection, we saw that since IC is equals to 36.5 degrees, so I dash must be greater than this critical angle, that is 36.5 degree. Now again, using this triangle, we can see that if the minimum value of I dash is equals to 36.5 degree, so the maximum value of R should be 90 minus 36.5 degree. That will give us a value of 53.5 degree. So maximum value of R should be 36.5 degree. Now we saw in this case that since this media and this outer covering apart from the glass core media is same with refractive index of 1, so we saw that for this angle I, automatically the angle of refraction is getting 90 degree. So for we can conversely say that I is equals to 90 degree for R is equals to 36.5 degree. Now the value of R is 36.5 degrees. So this value will never cross the maximum permissible value for any given value of I. So we can say that for every value of I, the total internal reflection will take place. The question says that the image of a small electric bulb fixed on a wall of a room is to be obtained on the opposite wall 3 meters away by the means of large convex lens. What is the maximum possible focal length of the lens required for the purpose? Now, in this diagram, we see there is a electric bulb on a wall and there is a convex lens which will be used to cast an image of this bulb on that screen or the wall. And the distance between this wall that is carrying the bulb and the screen is 3 meters. Now this distance is fixed. We have to find out what would be the maximum focal length for which we can cast the image on that screen. So here we will use the lens equation. So for maximum focal length, we will solve for f maximum. Now we have assumed u to be x variable, that is distance of the object or the bulb or the wall that is carrying the bulb from the lens as u equal to x. Now obviously the image distance will be 3 minus x because it is fixed. The distance between those two walls is fixed. Now using the sign convention and the lens formula and substituting the values in this equation, we will see that 1 by v becomes 3 minus x, and since v, the screen is on the right hand side, it is going to be positive, so it would be 3 minus x, minus u is on the left side of this lens, so it is going to be negative. So I have substituted 1 by minus x equals to 1 by f. So using the values u equals to x and v equals to 3 minus x, we have substituted the values over here in this lens equation. Now solving for f, we get the value of f as 3x times 3 minus x by 3. Now upon simplification we will get f as x minus x square by 3. Now for fx to be maximum, for this focal length function to be maximum, we know the mathematical condition, that is this one, f dash x, or the differentiation of the function of focal length with respect to x must be equal to 0, and the double differentiation of that function with respect to x must be less than 0. Now differentiating it for the first time with respect to x and equating it with 0, we came to the conclusion that the value of x is 3 by 2 or 1.5 meter. Now checking it for the double differentiation, we get the negative. That is, for the value of x as 3 by 2, fx is going to be negative. Fx is going to be minimum. Now since we know that we have used as 3 minus x, and we have got the value of x, that is u. So we have got the value of u and v as u equals to 1.5 meter and v as well as 1.5 meter. Now using those values in the length equation with proper sign convention, we come to the conclusion that 1 by f is equals to 1 by 1.5 minus of 1.1 by 1.5. Now upon calculation we will get the value of focal length as 75 centimeter. The question says that a screen is placed 90 centimeter from an object. The image of the object on the screen is formed by a convex lens at two different locations separated by 20 centimeter. Determine the focal length of the lens. So we have been given an object and a screen, and the distance of separation between them, that is 90 centimeter, and we have to find out what would be the focal length of this lens, given that there are two images, there are two positions for this lens where the image can be casted on this screen, and those positions are separated by a distance of 20 centimeter. So let us represent it by d, the position of the difference between the position of the lenses which can subtend the image on the screen. So let us assume that the first position, the distance of the object from the lens from the first position is u1, and the distance of the object from the second position is u2, and subsequently the image distance would be v1 and v2. Now we know that since this distance from the object and the screen is fixed, and that is 90 centimeter, so u1 plus v1 or u2 plus v2 equals. Now using these relations we have to find out the value of focal length of the lens. Now let us generalize this approach by saying the distance between the object and the lens wherever it is, either in the first position or in the second position, be x variable. So automatically the image distance from the lens would be 90 minus x, because the total distance is 90 centimeter. So v would be equal to 90 minus x. Now let us use the lens formula over here, that is 1 by v minus 1 by u equals to 1 by f. With proper sign convention we can write 1 by 90 minus x, that is v. Since v is in the right side of the lens, so it is going to be positive, and u, that is the object, is in the left side of the lens, so it is going to be negative. So 1 by 90 minus x minus of 1 by x equals to 1 by f. Since it is a convex lens, so focal length is going to be positive. Now simplifying this, we get the relation for focal length as 90 minus x times x by 90. Now for quadratic equation, so this is a form of quadratic equation which can be further simplified to is this x square minus 90x plus 90f equals to 0. Now in this equation there are two variables, x and f. So let us first take a look at the quadratic equation solutions. So for a quadratic equation ax square plus bx plus c, we know that the solutions are given by minus of b plus minus root under b square minus 4ac by 2a. So using this coefficients, we can write the solution for this equation as well, as x equals to minus of 90 plus minus under root minus of 90 whole square minus 4 times 1 times 90f by 2. So one solution will contain plus of this determinant, and another solution will contain minus of this determinant. We know that x is the solution for the value of u, that is the distance between the object and the lens. So we also know that the difference of this position that we have taken earlier, that is u2 minus u1, would be equal to d, that is this distance of separation, that is 20 centimeter. So we can simply write over here, then u2 minus u1 is equals to 20 centimeter, or the first solution minus the second solution is equals to 20 centimeter, or we can say that the distance
of the first solution minus the distance of second solution is equals to 20 centimeter. Let us use this relation to eliminate one of the variables among x and f. So we can write that u2 minus u1 equals to d, that is 20 centimeter, or we can say that the distance without any sign convention, we can write it as x2 minus x1 equals to d. So using this and substituting the values of the two solutions of x, we come to a value of 20. Under root of 90 square minus 4 times 90f is equals to 20. Now squaring both the sides of this equation, we will get the value of f as 21.4 centimeter. That's how we have found out the value of x. That's how we have found out the value of f, that is the focal length of convex lens. The question says that determine the effective focal length of the combination of the two lenses in exercise 9.10 if they are placed 8 centimeter apart with their principal axis coincident. Does the answer depend on which side of the combination a beam of parallel light is incident? Is the notion of effective focal length of this system useful at all? So, in the previous exercise of 9.10, we were given two lenses, a convex lens and a concave lens, and we were asked to find the F effective or the net focal length of the system. Now, in this question, it is asking that these two lenses are kept apart 8 centimeter. Now, we have to find out what would be the effective focal length, and does that hold any meaning at all. Here, we have to determine the effective focal length of the combination of the two lenses, and we also need to answer that will the effective focal length depend on which side of the lens the light is coming from, or which side of the lens the object is placed. And we also need to comment, is the notion of effective focal length of the system useful at all. Now here we can make two cases to find out whether the answer will depend on which side of the combination of the beam of parallel light is incident. We will first put concave lens on the back side of the convex lens, or if we imagine the rays coming from an object that is placed at infinite, or the rays are parallel. So at first we will put the convex lens on the left hand side, and then in the second case we will put concave lens on the left hand side and see will the answer depend. Now for an object at infinity on the left hand side, the image will form at the focus of the convex lens. Since we have been given the focus of 30 centimeter, so the distance of image from for this lens would be v equals to 30 centimeter. As u1 is infinity, u1 as in the case of convex lens, that is the first lens, we can say that v1 is equals to 30 centimeter, and u2 here represents the object distance for the concave lens, that is the second lens. When this lens is forming the image, it would be 30 centimeter on the right hand side of the lens. So 30 centimeter from this direction would be somewhere here. Now the distance of this image which will act as an object for this concave lens will be 30 minus 8, that will be equal to 22 centimeter. So for this lens, the object will be placed at 22 centimeter on the right hand side. So we can write u2 as 22 centimeter. Now using the lens formula for this second lens, we can find out the value of its v, that is the image formation, the position of the image. So using this lens formula for this concave lens, we can write 1 by v equals to 1 by f plus 1 by u, and 1 by u is 1 by 22 centimeter, and 1 by f is 1 by minus of 20 centimeter, because the focal length is given as 20 centimeter, and since it is a concave lens, we can write it as minus 20. So calculating this, we will get a value of v as minus 220 centimeter. So for this lens arrangement, we will get, when the object is at infinity, the final image will be forming at v equals to minus of 220 centimeter on the left hand side of this lens by a distance of minus of 220 centimeter. Now we will consider the second case in which concave lens is the first lens and the convex lens is the second lens. So here v1 would be equals to minus of f, because when the incident ray is there, it will virtually tend to form an image in front of the concave lens 20 centimeter or equals to its focal length. Now we can treat this image as a virtual object for this convex lens. So u2 would be equal to this 20 centimeter plus of this 8 centimeter distance. So the total value of u2 would be minus of 28 centimeter with sign convention. So again applying lens formula over here.
So we will get 1 by v equals to 1 by f plus 1 by u, and we saw that 1 by u is equals to 1 by minus of 28 centimeter, and since focal length is positive for the convex lens, so it will be 1 by 30. Calculating this, we will get a value of v as minus of 420 centimeter. Now we can comment that seeing this results that we changed from the previous case of 220 centimeters, so that we can say that yes, the answer depend on which side the incident ray is coming from, because v has changed or the final image distance has changed. And we can also comment that no, the notion of effective focal length won't work in this case, because there can't be f effective, as the image position is varying depending upon which lens, which side, or the which lens is receiving the first incident rays. Now the second question asked, like, an object of 1.5 centimeter is placed on the side of the convex lens in arrangement A above. The distance between the object and the convex lens is 40 centimeter. Determine the magnification produced by the two lens system and the size of the image. So now using this arrangement, we have been given the value of u, that is the object distance from the convex lens, and that is of 40 centimeter, and the object size or the height of object is given, that is 1.5 centimeter, and we have to find out what is the magnification produced by the two lens system, and also we have to determine the size of the image. So let's go to the calculation. So this is the arrangement that we were talking about. The object is placed in front of convex lens, and u has been given, and that is a value of minus of 40 centimeter. Focal length of this convex lens is 30 centimeter, and focal length of this concave lens is minus 20 centimeter, and the distance between these two lenses is again 8 centimeter. So we will consider this first lens and this as the second lens. So u1 would be equal to minus of 40 centimeter with the sign convention. So using lens formula for finding out the image produced by this convex lens, so 1 by v equal to minus of 1 by u, and that is u is minus of 40. So 1 by v equals to minus of 1 by 40, and that would be equal to focal length. Focal length of convex lens is positive, so it will be equal to 1 by 30. So calculating here v, we will get a value of 120 centimeter. Now we can see that from the pole of this lens, the image will form, the first image will form 1 centimeter on the right hand side of this lens. So this image will act as an object for this concave lens. So we can find out the object length, object distance from for this concave lens, and that would be equal to u2 would be equal to this 120 centimeter minus of this distance 8 centimeter, and that will come out to be equal to 112 centimeter. Since this distance is on the right hand side of the concave lens, so it is going to be positive, or u2 is going to be plus of 112 centimeter. Now applying the lens law over here, 1 by v minus 1 by equals to 1 by f. Here f is negative because it is a concave lens, and 1 by v minus 1 by 112 would be equal to minus of 1 by 20. So solving this for v, we will get a value of v as minus of 560 by 23 centimeter. That is, the position of image is on the left hand side of this concave lens at minus of 560 by 23 centimeter on the left hand side of this concave lens. So we have got this value of u1, v1 and u1, and v2 and u2. Now we can find out the magnification of each lens independently, and then we can find out the product of magnification so that we can get the net magnification. So magnification for the convex lens would be equal to m1 equals to 120 by minus of 40, as m is equals to v upon u. So we can divide it and get the value of magnification by the first lens as minus of 3, and by second lens similarly we will substitute the values in that formula, and we will get the value of minus of 5 by 23. Now net magnification will be equal to the product of these two independent magnifications, and that will be equal to 0.652. That is, the net magnification is less than 1 and it is diminished in size. So the final height of this image is going to be equal to net magnification multiplied by the original height, and that we will get solution as 0.98 centimeter, because the initial height was 1.5 centimeter. So we can multiply it with 0.652. That is a net magnification, and we will get the value as 0.98 centimeter. The question says that at what angle should a ray of light be incident on the face of a prism of refraction angle 60 degrees so that it suffers total internal reflection at the other face? the refractive index of the material of the prism is 1.524. So here we are being talked about the faces of prism A, B, C, and the faces that are in consideration are AB and AC. Now on the face AB, the incident ray ON makes an angle I of incidence with the normal, and it goes in the prism with the angle of diffraction equals to R1. Now it strikes the second face AC with an angle of incidence of R2, and it goes out with an angle of refraction as E, or angle of emergence. Now in our question it is said that on the second phase it should reflect such that total internal reflection happens, or the angle of emergence should be equal to 90 degree. So for that condition we have to find out what would be the value of I. So we know in a prism the angle between two faces are called the angle of refraction. The prism and it is given over here that it is 60 degree. So we also know the relation for prism that R1 plus R2, this R1 plus this R2 is equals to the angle of refraction of the prism, the angle between the two faces, and that would be equal to 60 degree over here. So R1 plus R2 equals to 60 degree. Now we will be applying Snell's law on these two faces AB and AC. So applying Snell's law on face AB, it would be equal to, if the outer media is having refractive index of mu1 and the prism is having refractive index of mu2, then it would be equal to mu1 sine I is equals to mu2 sine R1. So we can say that the mu1, or the refractive index of the media is, the media surrounding the prism is 1, and sine I would be equal to 1.524 times sine R1. Now applying Snell's law on the interface AC, that is the second phase, we could see that it is mu2 sine R2 equals to N1 sine E. N1 is the refractive index of the media that is surrounding the prism. Now for total internal reflection, as we discussed, E would be equal to 90 degree. So substituting the value, we will get sine R2 equals to 1 by 1.524. Now R2 would be equal to sine inverse of 1 by 1.524. This will give us R2 the value of 41 degree. Now substituting this value R2 equals to 41 degree in equation number 1, that was R1 plus R2 equals to 60 degree. We will get the value of R1 as 19 degree. Now substituting this value of R1 as 19 degree in equation number 2, we will get the value of I. So solving for the value of I, we will get the value of I as 30 degree. Thus for the angle of incidence of 30 degree, we will get the total internal reflection on the second face of the prism. The question says that a card sheet divided into a square, each of size 1 millimeter square, is being viewed at a distance of 9 centimeter through a magnifying glass. A converging lens of focal length 10 centimeter held close to the eye. Now what is the magnification produced by the lens, and how much is the area of each square of the virtual image? So the question is saying that there is a convex lens of focal length 10 centimeter, and in the front of convex lens there lies a sheet. Let us assume it over here, and it is 9 centimeter in front of that convex lens, and on the sheet there are divisions pattern of a square, each of area 1 millimeter square. So we have to find out what is the magnification produced by this lens and what is the virtual area, or the area of the image produced by the lens. Now how to approach this question? So the first thing over here is we have been given the value of object distance, that is minus 9 centimeter with the sign convention, and we have been given the focal length. So for the position of image, we can calculate the value of V. Now we also need to calculate the area of this virtual area of this square that would appear from the eye. So we need the value of magnification by the lens, and it is given by V divided by U, that is the position of image divided by the position of object. So here only V is the unknown quantity, and we can use the lens formula in order to calculate V. So we can get the value of magnification. Now the second question is saying that what is the angular magnification, magnifying power of the lens? So we know that the angular magnification and the magnification is different. We have to calculate angular magnification as well. And also the third question is the magnification in case A equal to the magnifying power or the angular magnification? Explain. So let us proceed with the unknown quantity V, that is the position of image. Now substituting the values we have been given, the value of u as 9 centimeter, and with side convention it would be minus 9 centimeter. Focal length as 10 centimeter. We will get the value of v as minus 90 centimeter. That is, the image is produced on the left side of this convex lens on the side of the object at 90 centimeter. Now we can calculate the value of magnification for the lens, that is v by u, and we will get 10. Now we know that the magnification produced is 10. So let us assume the virtual area of the square be a dash, and the given original area is 1 millimeter square. Now we saw that the magnification produced is 10 times, so 1 millimeter will appear as 10 millimeter. Now 1 millimeter square will appear as 10 millimeter cross 10 millimeter, that is 100 millimeter square. Since the linear magnification is 1 millimeter and area is having two dimensions, so we can say that 1 millimeter becomes 10 millimeter, and the area subtended by this 10 millimeter would be equal to 100 millimeter square. So the two questions are clear. Now let us move towards the angular magnification or the magnifying power. So we know that angular magnification is defined as the factor by which image on the retina gets enlarged. Now it is given by visual angle by the final image divided by visual angle by the object. And visual angle by the final image will depend upon the image position. So for this case, the image position is different than the value of d. So the angular magnification formula would be equal to d by f. So we can get the value of 2.8. Now there are cases when this magnification is going to be equal to the magnification produced by the lens, and in that case the image is formed at the least distance of distinct vision, that is equals to d. So in this case, what is happening is that image is forming at minus 90 centimeter. That is why this value is different from the magnification of the lens. Angular magnification is different from the magnification of the lens. If this value, if the position of v or the final image is minus of d, then we can say that angular magnification is equals to magnification of the lens. The question says that at what distance would the lens be held from the card sheet in exercise 9.22 in order to view the squares distinctly with the maximum possible magnifying power. Now here it is asking what is the distance of the object from the previous question, so that we can view the image properly with the maximum magnifying power. Now this question is taking the data from the previous question, and the data are focal length of the convex lens was 10 centimeter, and now here we have to find out the magnification, the magnifying power or the angular magnification for the image to be formed such that the eyes could see distinctly. So for the squares to be visible distinctly, the image should form at the least distance of distinct vision, that is 25 centimeter away from the eye. Now so that we can deduce from this is that v should be equal to minus of 25 centimeter. That is, the final image should be at least 25 centimeter away from the eyes. Now, so we have got the value of b, we have the value of f. Now we have to find out the value of u such that this case is met. Now here we have to find out what is the magnification in this case as well. Now here this magnification, the value of m is going to be equal to v by u, and whereas this is small m, the magnification is represented by small m, and the magnifying power is represented by capital M. So we have to find out the magnification as well. So we have to find out the value of u, so that we can use the formula v by u. Now we also need to comment that is the magnification equal to the magnifying power. Now we have to comment that is this magnification equals to the magnifying power. So we have the formula ready that is to be used, that is the lens equation. So 1 by v equals to 1 by v minus 1 by u equals to 1 by f. Now here 1 by v, we can put the value of v as 25 centimeter. With sign convention, it would be equal to minus of 25 centimeter. We have to find out the value of u, and the value of f is given, that is 10 centimeter. Now the value of u from this calculation is minus of 7.14 centimeter. Now here we know that angular magnification is given by d divided by u naught, or the distance of object from the object. So this is the angular magnification. It comes out to be a value of 3.5, and this is the magnification. So this can be given by v divided by u, and this is same as the angular magnification. Now here we have found the value of linear magnification in this case, and we saw that is the magnification equal to the magnifying power in this case, then we saw that the answer of this question is yes. Now how did this happen? How did the magnification become equal to the angular magnification? So we know that this now angular magnification is given as the visual angle formed by the final image divided by the visual angle formed by the object at D. Now this the formula for angular magnification is capital D upon U naught, where U naught is the object distance from the objective or the lens. Now linear magnification was given. Now magnification is given as V by U. Now here we saw that in this case when the final image is at D, then we can write V as 25 and U is the object distance. So we can write it U naught. So we can see here that M is equals to M. Capital M is equals to small m, or the angular magnification is equals to the linear magnification. So we can say that whenever the final image is forming at D, then we can get the angular magnification is equals to the linear magnification. The question is saying that what should be the distance between the object in exercise 9.23 and the magnifying glass if the virtual image of each square in the figure is to have an area of 6.25 millimeter square. Would you be able to see the squares distinctly with your eyes very close to the magnifier? So we have been given the desired the area of a square that is desired, and we have to find out the object position for the desired surface area. So we can say that A dash is 6.25 millimeter square, where A dash represents the area of the image. So we can deduce from this the length of each square. So length would be the square root of this area, which will give us 2.5 millimeter. Now we saw that in this question number 9.23, the length of each square and the width of each square was 1 millimeter. So upon magnification, it is going to be equal to 2.5 millimeter. So we see here that linear magnification is going to be V by U, which is the final length divided by initial length, that is 2.5. So we can say from here that V by U would be equal to 2.5. Now here we are desired to find this value of U. So now we have got the value of V in terms of U. We can write V equals to 2.5 U from this relation, and we know the focal length of this lens, which is 10 centimeter. So there is only one variable, that is U, to be used in the lens equation. So we can find out the value of U. Now later we have to say that we have to comment on would you be able to see the squares distinctly with your eyes very close to the magnifier. So for this value of U, will we be able to see the squares distinctly with your eyes? Now in order to see the squares distinctly, the minimum distance should be equal to D. So let us find out whether U is greater than D or whether U is less than D. If U is less than D, then we won't be able to see it, and if U is greater than D, then we will be able to see the squares distinctly with our eyes. So let's use the mirror equation. Let's use the lens equation to find out the value of U first. So 1 by V minus 1 by U would be equal to 1 by F. Now 1 by V in terms of U is equals to 2.5 U. Now 1 by U is as it is. Now 1 by F would be equal to 1 by 10. Now the value of U calculated is minus of 6 centimeter. That is, the object should be 6 centimeter away from the objective or the magnifier. Now here we can see that the least distance of distinct vision is 25 centimeter, and U for this desired area is minus 6 centimeter. So U is less than D. So we can't see the square distinctly. The question says that an angular magnification magnifying power of 30x is desired using an objective of focal length 1.25 cm and an eyepiece of focal length 5 cm. How will you set up the compound microscope? So basically it is asking that what would be the length of this microscope if we have got an objective of focal length 1.25 cm and an eyepiece of focal length 5 cm. So we know that the length of microscope can be given by the distance of the image from the objective added with the object distance for the eyepiece. Now we have also been given that the desired magnifying power is 30x. So we can write it as m equals to VO by UO, that is the position of final image by the objective divided by the object distance from the objective multiplied with 1 plus d by FE, where FE is the focal length of the eyepiece. Now in this expression, this first part is magnification by the objective and the second part is the magnification by eyepiece. Now it is desired that m would be equal to 30, and let us calculate the expression for ME first, the value for ME. Now we have been given that the focal length of the eyepiece is 5 centimeter. So substituting the values, we will get the value of ME, and that would be equal to 6x. Now we can substitute this 6x in this formula and find out the value of MO. Now finding the value of MO, we will get the value of 5. That is magnification by the objective is going to be equal to 5 times. Now we know that objective creates virtual image, so we can write it as -5. Now the magnification by objective is given by VO, that is the objective, the image, the position of image produced by the objective divided by the object from the objective lens would be equal to -5. So if we assume that UO, that is the object distance from the objective, is -x using the sign convention, then VO would be equal to 5x using this relation. Now using lens equation for the objective, we will find out the value of UO. So substituting the values that we assumed in the previous case. So 1 by V would be equal to 1 by 5x. Now 1 by U would be equal to 1 by x because U is -x. So finding the value of x, we will get the value of 1.5 centimeter. Now since we assume that VO is equals to 5x, so VO is going to be equal to plus of 7.5 centimeter, and UO, that is the object distance from the objective, is going to be equal to minus of 1.5 centimeter. So we have got the value of UO over here and the value of VO over here, and we also know that we have to find out the value of VO and UE. So only unknown quantity is the object distance from the eyepiece. We have the value of VO, that is 7.5 centimeter. Now let us find out the value of UE. Now for finding UE, we will use the lens equation for the eyepiece. So for finding UE, we have been given the data, that is final image will be at -d under normal adjustment. So it would be equal to minus of 25 centimeter, and focal length is given, that is 5 centimeter. So just we need to find out the value of U. We can use lens formula in this to find out just one variable. So using the lens formula, we will get the value of U as 4.17 centimeter. So the object distance from the eyepiece is going to be equal to 4.1 centimeter for the magnification of 6x. Now we have got the value of UE, that is this one, and we calculated earlier the value of VO. Now we can add it to get the length of compound microscope, and similarly we can substitute the values and find out the answer as 11.67 centimeter. The question says that a small telescope has an objective lens of focal length 140 centimeter and an eyepiece of focal length 5 centimeter. What is the magnifying power of the telescope for viewing distant objects when the telescope is in normal adjustment, that is when the final image is at infinity and the final image is formed at the least distance of distinct vision, that is 25 centimeter. So here we have been given two cases where the final image is forming at infinity and the final image is forming at the least distance of distinct vision, that is 25 centimeter. And in both the cases we have to find out what would be the magnifying power for the telescope. So we know that the expression for finding the magnifying power, or the formula for finding the magnifying power, is given by, if the image is forming at infinity, then it is given by focal length of the objective divided by focal length of the eyepiece. Now, if we use this formula, we will get the answer for first case, that is the telescope is in normal adjustment, then its magnifying power would be equal to 28 times. Now, similarly, for the case where the final image is forming at D, the formula is given by focal length of the objective divided by focal length of the eyepiece multiplied by 1 plus Fe by DE. Now, using this formula, we get a value of 33.6. So, we see that the magnifying power in second case is greater as compared to the first case, or magnifying power when the final image is forming at the least distance of distinct vision is greater as compared to when the image is forming at infinity. The question is saying that for telescope described in exercise 9.27a, what is the separation between the objective lens and the eyepiece for the final image forming at infinity? Write the separation between the objective and the eyepiece as focal length of the objective plus focal length of the eyepiece, and that will be equal to 140 centimeter plus 5 centimeter, and which will give us 145 centimeter. Now the B part of this question is, if the telescope is used to view 100-meter tall tower 3 kilometer away, what is the height of the image of the tower formed by the objective lens? So let us move to this question. Now we assume that this is the convex lens or the objective with a focal length of 140 centimeter. Now here lies the image. Now we can see that if the image is lying beyond the center of curvature, first center of curvature of the lens, so the image will form between the focus and the center of curvature, and if the object is placed far beyond, then the image will tend towards the focus, the second focus. So here we see that the angle made by the object and the image is going to be same. Here it is denoted by theta 0 or theta naught for the object and theta I for the image. Now here we can see that the image distance or the V would be equal to approximately would be equal to F, because 3 kilometer is too much as compared to the focal length of 140 centimeter. So we can write that theta naught would be equal to theta I, and theta naught can be given by height of the object divided by the base, that is 3000 meter, and the theta I for theta image is given by height of the image by focal length of the objective. Now equating these two angles, we will get the value as HO by 3000 would be equal to HI by FO. Now HI would be equal to 0.047 meter or 4.7 centimeter. So height of the image would be equal to 4.7 centimeter in this case. Now the third question follows. What is the height of the final image of the tower if it is formed at 25 centimeter? So given the same arrangement that the image height is 4.7 centimeter, we have to find out what would be the final image height, what is the height of final image if it is formed at 25 centimeter from the eyepiece. So here in this case for the eyepiece, we have been given V, that is the final image position, that is 25 centimeter. We have been given the value of F, that is focal length, that is of 5 centimeter. Using this lens equation, we can find out the only unknown, that is U, object length or object position from the eyepiece. So calculating U, we will get a value of 25 by 6. Now we have to calculate the height of image, final image. So height of final image can be given by the magnification formula, linear magnification formula, that is V by U. And since we know the value of U now, that is 6. So the height of image can be calculated as the height of image by the objective, or the height of the image formed by the objective multiplied by the magnification of eyepiece, and which will give us 4.7 times 6, that would be equal to 28.2 centimeter. Thus the magnitude of the height of the image, the final image produced, is 28.2 centimeter. The question says that a Cassegrain telescope uses two mirrors as shown in figure 9.26. Such a telescope is built with the mirrors 20 mm apart. If the radius of curvature of the large mirror is 220 mm and the small mirror is 140 mm, where will the final image of an object at infinity be? So when the object is at infinity, what is the position of final image? We have to calculate this. Given that the focal length of the larger mirror, I have denoted it as 1, is given as 110 mm. We have been given the radius of curvature, so we can deduce the focal length from that, and which will be equal to radius of curvature divided by 2. So focal length of the larger mirror is going to be equal to 110 millimeter, and the focal length of the smaller mirror is going to be equal to 70 mm.
and they are positioned 20 mm apart. So for the object at infinity, the image formed by the first mirror is going to be at the focal length of the first mirror, and since the focal length of first mirror is 110 mm, so the image position is going to be equal to minus of 110 mm. I have denoted it as V1. So the value of OV1 is going to be equal to minus of 110 mm. Now this image is going to act as a virtual object for this second mirror. Now since second mirror is positioned 20 mm in front of the first mirror, so the object position for this second mirror is going to be equal to 110 minus of 20, and with sign convention it is going to be equal to minus of 90 mm. So for this second mirror, we had to calculate the position of final image, that is V. So in this mirror formula, we haven't given the value of F, and we know the value of U now, that is equals to minus of 90 mm. So we can easily calculate the value of V. So let's calculate using the mirror formula. So 1 by V plus 1 by equals to 1 by F, and 1 by V would be equal to 1 by F minus of 1 by U, and minus of 1 by 90 would be equal to plus of 1 by 90, and thus calculating we will get the position of final image, and that is 315 millimeter in front of the mirror of the smaller radius. The question says that light incident normally on a plane mirror attached to a galvanometer coil retraces backward as shown in figure 9.29. A current in the coil produces a deflection of 3.5 degrees of the mirror. What is the displacement of the reflected spot of light on the screen placed 1.5 meter away? So when light reflects off a mirror, the angle of incidence equals the angle of reflection. Now angular deflection by the reflected ray, if the mirror rotates by an angle theta, the reflected ray rotates by an angle of 2 theta. It gets deflected by the magnitude of 2 theta. So imagine that this solid black line is the mirror in the initial case, and this red line is the normal to this mirror, and it is reflected by it is tilted by theta degree. Then the reflected ray, this blue line, will get deflection of 2 theta degree. Now, if we assume that this is the length between the screen and the mirror, L, then the deflection is given by small d equals L times tan of 2 theta. Now, in this case of galvanometer, theta is equals to 3.5 degree. So, 2 theta would be equal to 7 degrees. And L is given as 1.5 meter. So, substituting these values in this formula, we will get the value of deflection as 1.5 times tan of 7 degrees, which will give us 18.4 centimeter. The question says that figure 9.30 shows an equiconvex lens of refractive index 1.50 in contact with liquid layer on top of the plane mirror. A small needle with its tip on the principal axis is moved along the axis until its inverted image is found at the position of the needle. The distance of the needle from the lens is measured to be 45 centimeter. The liquid is removed and the experiment is repeated. The new distance is measured to be around 30 centimeter. What is the refractive index of the liquid? So in this arrangement, there is a lens and there is a liquid layer, and this is a plane mirror. Now there are two cases. In one case, there is a liquid layer of some refractive index that is unknown, and we have to find out that refractive index. And in another case, the liquid layer is not present. So in the case when the liquid layer is present, the image of a pin that is on the position PQ is formed on the same position, and in the case when the liquid is not present, the same repeats as well. The only change is the distance between the object and the lens and mirror system. So in the case when the liquid is present, the distance is 45 centimeter, and the case when the liquid is not present, it is 30 centimeter. So this is a question of the combination of lenses and also the reflection of a plane mirror. So we know that a position of image in the case of plane mirror is same in magnitude as that of the object, that is u equals to v. And if the object is real, virtual image is formed, and if the object is virtual, real image is formed in the plane mirror. Now here, in both the case, with or without the fluid, the object is virtual for the plane mirror, so the real image is formed, which is being superimposed on the object. Now, if we remove this mirror, the question is very much simplified, the sign convention. Like if we remove this mirror, the image that was forming on the left hand side of this lens system will form on the right hand side of the lens system, we can simplify this question by changing the sign convention of V to a positive, because if there was no any plane mirror, then the image would have formed on the right hand side. And also plane mirror does nothing with the magnification, it only, and also the position of image remains same, that is the magnitude remains same from the object, the image forms at the same distance. So let us assume the case when there is no any liquid. So when there is no any liquid, then we can calculate the focal length of this lens as 1 by focal length of the lens would be equal to n minus 1, 1 by r1 minus 1 by r2. This is the lens maker's formula, where n is the refractive index of this glass that is used to make this lens, and r1 is the radius of curvature of this side, and r2 is of this side. R1 would be positive because its center of curvature would lie on the right hand side of this lens, and R2 would be negative, and they both are of same radius of curvature, so we can write it as R, and thus we will get 1 by F lens is equals to 1 by R. Now in this case, without the liquid, the image and the object were at 30 centimeter in front of this lens. So we can assume that V equals to 30 centimeter when there is no any plane mirror, and when there is plane mirror, then V would be equal to minus 30 centimeter. So for simplification, I have just removed this plane mirror, so V would be equal to 30 centimeter and U would be equal to minus 30 centimeter. So using lens equation now, we will get the value of R or F. Since F of this lens is equals to 1 by R, so we can easily write that 1 by 30 plus 1 by 30 equals to 1 by R. This will give us R equals to 15 centimeter. That is the radius of curvature of this lens is equals to 15 centimeter. Now we will proceed with this case when there is a liquid. Now when there is liquid, then the refractive index of this liquid be mu2. Then now it is a combination of two lens system, that is this lens of glass and this is the lens of this liquid. And for this glass we already know that the focal length of this glass I have represented it with 1. So the f1 by f1 would be equal to 1 by r, and we have now 1 by f2 would be equal to mu2 minus 1 by r1 minus 1 by infinity. Since other side is infinity, so other side is plane for this liquid, so we can say that it would be 1 by infinity. Now R1 for this would be this side, which is equivalent in magnitude with this one, and its center would lie on the left hand side, so we can write it as minus of 1 by R, which was calculated in the previous part. So we can easily write as R1 as minus of R. Now substituting 1 by R1 as minus of 1 by R, we can get that 1 by F2 equal to mu2 minus 1 minus of 1 by R. Now we would get that 1 by F2 would be equal to 1 by R into 1 minus mu2. Now we will calculate the equivalent focal length. So we know that equivalent focal length is equals to the addition of inverse of the focal length, since they both are in contact and they both are thin lenses. So we can write as 1 by F equivalent would be equal to 1 by F1 plus 1 by F2. Now 1 by F equivalent would be equal to that of the glass and that of the liquid. So this is one that contains the liquid focal length. We have calculated it just now, and this is one for the glass focal length. So 1 by F equivalent would be equal to 1 by R times 2 minus mu2. Now this is the F equivalent for the case when the liquid is present between the lens and the plane mirror. Now again we will assume that there is no any plane mirror, because the plane mirror is only changing this direction of V. If there is plane mirror, then V is equals to minus of 45 centimeter. If there is no plane mirror, then V is equals to plus of 45 centimeter. Now we will apply the lens equation again with F equivalent. So using the values, 1 by V would be equal to 1 by 45 and U would be equal to minus of 45. So minus of 1 by U would be equal to plus of 1 by 45. And this we just found out. And substituting the values of R, we will solve this equation, and then we will get mu2 would be equal to 2 minus 2 by 3, and which will be equal to 1.33. That is, the value of mu2 would be equal to 1.33. Thank you.